Okay, as I promised yesterday, so today I am going to discuss the evolution problem associated to the same equation we analyzed yesterday. Of course, I insist I am focusing on quite a special model case, but it's still very instructive to my opinion. And I will just focus on zero Dirichlet condition, but really most of the things could be similar for a non-homogeneous boundary condition. Let me recall, for me, omega is a bounded and smooth set in Rn. P is strictly bigger than 1, so we are in the superlinear case. F and U0 are regular. And I'm not doing any sign condition on U0 and F, which means that somehow I could reverse the sign of the nonlinearity by switching U into minus U. But at some point I will fix, of course, just to fix the ideas in what I will say. The problem I will discuss is blow up, essentially, or long time behavior, and what kind of emerging patterns we can see. And there is a related problem here, which is the singular limit in the stationary case. So yesterday I discussed this problem that for lambda positive admits a solution, but not always for lambda equals to 0. And so the long time behavior is associated to the singular limit, what happens when you drop the 0 order term in the equation. And in fact, there is quite a classical relation between those two limits, the long time behavior and the lambda, the singular limit. So these problems 1 and 2. Problem 1, when t goes to infinity, is related to problem 2 when lambda goes to 0. And just to mention a little bit why this problem is called also ergodic problem or related to ergodic problem. So what is in dynamical systems, what is an ergodic type behavior? So here the dynamical system is the, say, stochastic process xt, which, if you remember, I mentioned yesterday, gives rise to a representation formula for the solution U. So U can be represented. So here, this is even for uncontrolled case. So it's a free stochastic process x tau, and which, of course, is associated to an operator. In this case, would be the Laplace operator, for example, if x tau is a Brownian motion. So you have a representation. So what is traditionally an ergodic behavior? For any dynamical system, an ergodic behavior means that if you take evaluation f along the trajectory and you take the time average, you see 1 over t integral between 0 and t, and then you do the long time average somehow, the ergodicity means that this limit essentially is independent from the point you started and can be represented from the spatial mean, which is usually the mean of f with respect to the invariant measure. So time average is somehow described by space average. That's a kind of ergodic behavior. And if you consider the stationary U lambda is just represented as a discounted evaluation of f, discounted with this factor lambda. And what is called in dynamical systems a kind of abelian tauberian theorem is that if you take the discounted problem here, you multiply by lambda and you take lambda goes to 0, then this limit should coincide with the long time average. So it should be the same as U divided by T. And for those interested, essentially, there is a very nice presentation of these properties in papers by Mariko Arisawa and also jointly with Louis Lyons. Okay, I want to mention an example which is probably clarifying things, I hope, for you. Suppose, again, this is not a controlled process. This is a diffusion drift linear equation. And suppose we are in the periodic case. Okay, so if we are in a periodic case, then there exists a unique constant C0 for which you have a periodic solution here. What is C0? Well, for example, if B is divergence free, you just integrate this equation on the period, on the reference period, and if B is divergence free, all those terms integrated become zero, and then you see that the constant that needs absolutely necessarily to be just the average of the function f on the period. So this is typical in homogenization problems, in periodic problems, that you need to adjust somehow, for example, the average of the source in a way that you can solve the problem. But then, still in the periodic case, you realize that once you have a solution of the stationary problem, you just consider V plus C0t, and you adjust plus or minus a constant, and you easily build sub and super solutions to the evolution equation. So if you divide by t this relation, you realize, you see that u divided by t must converge to this constant C0. And this is the typical relation between the long time behavior and this appearance of this constant in the periodic case. And in general, you also can prove that if you drop this, say, linear in time shift, then you observe u minus C0t should behave like this function v. So you see that somehow it's a kind of traveling wave, if you want, but it's a trivial somehow traveling wave because it's just a sort of stationary function which then moves in time with velocity c0. This is what happens in the periodic case. But now, if you believe that something similar occurs for the Dirichlet problem, then you would guess that in case of Dirichlet conditions, if you should behave or would behave like C0t, then at a boundary, since this would mean that you should go, roughly speaking, to infinity. Okay, it could be positive or negative depending on the sign of C0. And this is why in this story we will see, as I was mentioning, that the long time behavior would be related to the maximal solutions that blow up at a boundary. Okay. Now I will focus on P between 1 and 2, and I will clarify this fact, because, to be honest, this cannot happen now for the Dirichlet problem in linear problems. The reason is why for the linear problem, the Dirichlet problem is always solvable. But for nonlinear problem, the Dirichlet problem is not always solvable, as I mentioned yesterday, and this is why we will see this kind of phenomenon. Okay, but let me mention first something for the evolution problem. First of all, this is, of course, very well known. If data f and u0 do not have any problem of regularity, if they are bounded, for example, then for p smaller than 2, there is a nice local theory of bounded solutions, and bounded solutions are smooth. I mean, this local theory in L infinity works in great generality, and from the papers also by Boccardo, Mira, and Puel. And then there is maximum principle. If things are bounded, then maximum principle says that U stays bounded. And also, there is smoothing effect, which means that the gradient becomes also bounded immediately, say, after a while. And you may quantify that exactly like in heat equation, if you want. And again, this is again due to the fact that P is smaller than 2, or that I'm saying would not be true for P strictly bigger than 2. But in this case, you have global existence for the evolution problem. So in fact, if you want to know what happens, there is either long time convergence, or there could be infinite time blow up of the L infinity norm. Okay, so here there is a mistake, I'm sorry here, because of course the L infinity norm of U depends on the L infinity norm of F also with time. So you see, it's like here, there should be here some dependence on time before, say, the function F. And this is why you might have infinite time blow up. And okay, so U is always controlled from above here, which means that U is a subsolution of the heat equation, and so U is controlled above. This depends from the fact that now I have put my nonlinearity in the left, which means that if blow up occurs, then U should go to negative infinity. And if U is behaving like a constant times T, this means that the constant must be non-positive, smaller than or equal to 0. So the heuristic is quite easy. If we guess that U should behave like C0 times T plus a stationary function, then the constant should be negative. And since U is 0 on the lateral boundary, this means that in the limit, V should be U minus C0T should go to plus infinity. So V should be a maximal solution of the type I discussed yesterday. And this is why the eventual possible blow up at infinity of U, linear in time, should lead to maximal solutions of the stationary problem. Okay. Let me recall a couple of things from what I said yesterday. So first thing, there exists a unique constant C0 such that there exists a boundary blow-up solution for this problem. Okay, so there is no lambda V here, and yesterday I said this was proved by Lafrie and Lyons. There is only one constant which makes this problem solvable, and also V is unique up to an additive constant, kind of additive eigenvalue, exactly. But then I also mentioned that this additive eigenvalue characterizes completely the solvability of the Dirichlet problem. If you wonder whether there is a stationary solution for 0 boundary condition now, then this happens even only if the above constant C0 is strictly positive. Again, like it happens.
Alessio,
yes.
Do you consider without any initial data? You consider equation without initial data, all global solution, which can grow when x to in the beginning, which grows to when x tends to infinity. Domain. Domain is
bounded.
Bounded. And,
domain is bounded here.
Yes, but no, if initial data is bounded, then solution also remains bounded without any initial data.
No, okay. The solution, yeah, okay, but if it depends on F, the solution can grow.
Yeah, I understand. If F more or less good, that if F is very large, I understand. But without any connection with initial data in parabolic setting.
Yes.
Yeah.
Okay. Yes. And this is probably again clarifying also your question. So now we
globally.
Yes, now we go back. Yes, there always exists a global in time solution, and we are discussing now what happens when T goes to infinity. And because we are maybe this answers your questions. Even I don't know if I got it. We are with P smaller than 2 or equal than 2, so any bound in L infinity immediately gives existence for the parabolic case. Yeah. So now let me assume a little bit more on F. For example, F is Lipschitz. I'm not at all questioning the regularity of the data in this story, nor yesterday, nor today. And this is a theorem we proved with Barl and Tabet-Chamba in 2010. So if that constant C0 is positive, then as you expect, there is a stationary solution and there is convergence in long time. U of T converges as T goes to infinity to the stationary solution. But if there is no stationary solution which corresponds to C0 negative or 0, then U of T blows up in any point of the domain, complete blow up. And actually, you we will be more precise later, but actually U behaves like C0 times T. So actually U divided T converts locally uniformly to a constant. Actually, when you have convergence to the stationary solution, the convergence is at exponential rate, if you are interested in that. But this is a minor point.
I'm sorry, Alessio, yeah. And I want to ask, how about C0 equal 0, C0 equal 0, and
yes,
how we can make sure that one convergent to minus infinity?
Yes, yeah, I will be more. Yes, I mean this. I will be more precise later.
Okay.
I mean,
I see.
That, okay.
Good.
Yeah. Okay. So, in fact, in any case, I mean, it is of course you cannot read. I mean, of course, here if C0 is 0, of course you only read that U divided T goes to 0. But I can tell you, I mean, more that even when C0 is 0, you must go to negative infinity everywhere. Negative infinity.
Yes. Because it is absorption only for positive solution. For
exactly. Absorption leads to negative infinity. Reaction would lead to positive infinity. But you can switch the sign and the result, of course, you can use it. Okay, so this is a more precise picture. When C0 is strictly negative, so there is actually some difference somehow, and also if P is between 3α and 2, then we can show even more. So we can describe somehow the profile. We can say that U minus C0T converts to this boundary blow up solution. So you see in this case, it happens like a little bit like in the periodic case. You have a stationary profile which travels in time with speed C0, and U is just a sort of translating profile in long time. This we can only prove this when C0 is negative and if P is strictly smaller than 3α. And quite surprisingly, in fact, we can show that this result is somehow optimal in the sense that if P is less than or equal than 3α, or if C0 is 0, we have examples where this convergence fails in the sense that U minus C0T goes to negative infinity and we don't have this kind of convergence. In fact, this is a new threshold, this 3α, that in the periodic case, for example, you wouldn't expect this always. The first kind of behavior is what I described before in the periodic case. But here, why this occurs, this new threshold, is because the blow-up rate is influenced by the singularity of the boundary blow-up solution. And this is the main point I want to describe now. And as far as the negative cases, of course, I must say that we don't have a totally clear picture, because I'm not saying that in this situation it always happened that the answer is negative. I can only say that the statement I does not hold in the same generality, does not always hold, and we have examples, for example, in star-shaped domains, where under some condition, for example, you see this is a typical condition when we can show the 2i holds. This condition means, for example, that f can be in size very, very big, for example, very negative, but with a small oscillation, for example. And okay, but this is quite a bit technical. Okay, very special. Okay, so let me describe why 3α plays a role. So this is a kind of what we would call in other maybe situations matched asymptotics. So we expect somehow that U minus C0T should probably behave like this boundary blow-up solution. So what we do is that we, of course, you see, we retrace C0T to our solutions. And we know that this translation U tilde satisfies more or less, say, the same evolutive equation as for the boundary blow up in the limit, but it's not still infinity at the boundary. Because of the Dirichlet condition, this U tilde is minus C0T, so it is going to infinity. Okay, so one expects that this is not exactly V, but there are error terms which depend on time. Okay, there are further ingredients, but I will focus on this estimate. So I'm dropping a little bit these further ingredients, and let me go to the error estimate. And what we prove, in fact, is that when C0 is negative, we can prove that U minus C0t is bounded in this range of P, and is still unbounded. So there is a sort of error term which is still unbounded when P is 3/2 or smaller than 3/2. And when C0 equals 0, also the difference between U and C0t is unbounded. So, of course, all the problem is the bound from below. And so all the problem is construct a subsolution by using the graph somehow of the boundary blow up as a sort of propagating front.
Yes,
So
yes.
what we do, in fact, is something like that. So let me focus, for example, on the star-shaped case. It's just to fix the ideas. It's simpler to see. So of course, if we have our omega, what we do a kind of dilation, you see. So we take the boundary blow-up solution V. So V is a boundary blow-up solution. Then we dilate a little bit with this R of t. And if R of t is smaller than 1, then now this V blows up in a slightly larger domain, which is this external domain. And this is omega divided R of t is slightly bigger than omega. And then what we do, then we let somehow this boundary blow up come inside in omega. And of course, we need to scale. This is useful for the equation. And then we let R go to 1. And this is like letting the graph of V somehow moving back to the original domain omega with some velocity, with velocities 1 minus R over t. Okay, so it's a typical front moving. And of course, what is the choice of RT, the velocity at which we move this graph? Well, of course, we want this dilation to be comparable with U minus C0t at the boundary. So in particular, if U is Dirichlet, so U is 0. So what we want is that this moved graph, we want it to be approximately exactly minus C0t on the boundary. This would be U is 0, so this would be U minus C0t on the boundary. This is matched asymptotics, if you want. We would like that this graph more or less matches with what we expect is the behavior of U minus C0t. But we know how V is blowing up at a boundary, because we know that, and this is the crucial point, we know that V behaves, for example, like a negative power of the distance. I explained that yesterday. Of course, if P equals 2, this is logarithmic, but let me do the case P strictly smaller than 2, because it's more uniform. So for P strictly smaller than 2, V behaves like a negative power. So we plug this asymptotics here. We want, this means that this behaves like 1 minus R of t to the negative alpha. And now we want it to be comparable to minus C0t, and this gives the velocity of 1 minus R. And 1 minus R is a big O of t to the minus 1 over alpha. And now we go to the equation. Why? Because, of course, we want also to compare the equations. So this moved front, which is here, we put it into the equation. We have the correct scaling. So we do some computation, and we end up with the original F minus C0 that we wish. And there is correction term. This correction term in first approximation is linear in 1 minus R. There is also a term with R prime, but this will be negligible in the end. So actually, when we compare, we build this solution, and this is like F. So C0 has now been brought in the left. So now this is like F plus an error, which is of the order of 1 minus R. So if we want a sub or a super solution, we need to drop off this term, which means that we just perturb V tilde by translation with a purely time-dependent function. And this is just the primitive, of course, of this 1 minus R. And this is now comparable with U minus C0t. Okay, so we compare actually U minus C0t, not directly with V tilde, but with this correction of V tilde, and then we know all the velocities because 1 minus R was at the order of minus 1 over alpha. And so this gives all the bounds that I told you before, in particular those bounds here. This gives the asymptotics of the second term in the expansion U minus C0t. And this gives positive results, but also the negative results, for example, in the star-shaped domains that I mentioned. Because in star-shaped, we can be a little bit more precise with this. Otherwise, in non-star-shaped, the problem is that this kind of idea must be localized. And this is why we don't have, a fully, clear picture. But so we see, for example, that U minus C0t is bounded if and only if this alpha here is smaller than 1, and this leads to P bigger than 3 alpha. And this is where, and this is completely dependent on the boundary blow-up rate of the solution. Okay, so there is a similar, actually, asymptotics also for the so-called stationary singular limit when lambda go to 0. So this is absolutely in parallel. I must say that we proved the evolution case before with the Barl and Tabet-Chamba, and then in a paper later, I saw that people were still interested in what was happening in the stationary case, but the spirit is very, very similar. And if you want to consider the limit when lambda goes to 0 here, so these are Dirichlet problems, stationary, then again, if C0 is positive, you have convergence to the stationary solution, which exists in that case. Otherwise, if C0 is negative or 0, you have complete blow up, in this case blow down, because U goes to negative infinity inside. You have the convergence of lambda U lambda to the constant C0. And if you just consider U lambda plus the L infinity norm, which in this case means that you are essentially translating the minimum value of U lambda, because U lambda is becoming very, very negative. So this L infinity norm is essentially minus the minimum. And then you get that this converges locally uniformly to the solution of to the boundary blow-up solution. Okay, so this is a little bit more precise than in the evolution case, because we don't have somehow this. It's a slightly simpler setting. And I want to go back a little bit on the explanation in terms of stochastic control, which explains why this is going to happen. So this is for the stationary, but you can give a similar explanation also for the evolutionary. So what is the stationary solution, as I was saying, corresponds to the discounted say optimization problem up to the exit time from the domain. So you see, if F is bounded, what happens is that when lambda goes to 0, actually U lambda would remain bounded unless the exit time is going to infinity. And this is why somehow you see coming into play, into the game, the state constraint condition, which means that the process does not exit the domain. And the spirit in the optimization is quite clear. Suppose that F is very negative inside, then you want to optimize, you want to minimize. So if f is very negative inside, what you wish to do is to try to catch those subsets inside where f is negative. So you would like to push, you are controlling your process, you would like to bring your process inside more, the more time as possible. And so if you can do that for the whole time, of course, you are happy. Okay, and okay, so this is probably half of what I wanted to say, and this gives essentially the long-time behavior and this kind of ergodic behavior for p smaller than 2. And now I want to describe the case that p is bigger than 2. We will soon need to accept that this is a much different case, but I will start from what is different, but also something which is similar. So first of all, there is a big difference to mention immediately, is that there is no local theory, no well-posedness local theory in L infinity here because of the super quadratic growth. So in fact, the local theory needs more regularity. For example, Lipschitz solutions. And this is why now when p is bigger than 2, somehow you can only say that if you want to solve, say, classically, or if you want to consider solutions that really are zero on the boundary, you need to start with a classical theory in C1. So, for example, you can say, okay, if U0 is C1, then there exists a local existence and uniqueness result. So there exists a maximal classical C1 solution, but this time T star can be finite, okay? So there could be blow up of the C1 solution. At the same time, of course, you still have the maximum principle, okay? So, okay, this is for the, I'm sorry, again, this is for the case that f is 0, but it's still interesting in this context. The case that f is 0 is still very interesting, and I will say a lot of things for that particular case later. Okay, so there is maximum principle, so you can remain bounded, but the problem is that the C1 norm can blow up. So there can be a time T star where the gradient blows up. And this is what is called in the theory of, say, evolutionary blow up. This is called just a gradient blow up phenomena. The solution remains bounded, but the gradient blow up. So it's really the C1 norm that blows up. And there are a lot of contributions in many different problems. I mean, I just mentioned problems which are of this kind or similar to this kind by people like, for example, Fila and Lieberman or Conner Grant. These are very classical contributions to the blow-up theory in parabolic equations. And of course, Philippe Souplé has worked a lot on that. And there is a book by Quittner and Souplé, which I strongly recommend to all that want to follow these classical blow-up issues. This gradient blow-up, we also know something more on this gradient blow-up. And for example, papers by Souplé describe that. First of all, that this gradient blow-up certainly occurs for suitably large initial data. So you see, it's not even a matter that the initial data is singular or not. You may take even very smooth initial data, but in size, if they are too large in size, then the gradient blow-up will occur. I will come back on that quantitatively a bit later. Then the gradient blow-up also can only occur at the boundary. That's very important. And this is a consequence of what we have seen yesterday. So let me give you a very easy, short proof. Maximum principle says that U is bounded for all times, at least for finite times. And the time derivative by translation if you, by translation, you can show that the time derivative somehow also is bounded from the time derivative at some previous point. So you may take very, very small t0 so that the time derivative is controlled, and then the time derivative would also be controlled. But then if you look at the equation, the time derivative can be somehow embedded into f. So it seems that at any time u satisfies a kind of stationary equation with some bounded f. Okay, this is not the original f. It should be f plus or say minus actually ut, but it's an f tilde which is bounded. And then we have seen the gradient bounds yesterday, stationary gradient bounds. So u inside is actually the gradient is controlled. So this means that somehow you would expect blow up of the gradient only at a boundary. And this can be made even more rigorous if you are in the framework of viscosity solutions, because there is this result by Barl and Dalio in 2004, quite surprising somehow result, but this is for generalized viscosity solutions. This is a result of existence and uniqueness for all times of a continuous viscosity solution. It will even be a Hilbert continuous a posteriori, but admitting the possibility that this solution does not take the value 0 at a boundary. So these are called the relaxed boundary condition, and this is a generalized viscosity solution, which means that, okay, if the nonlinearity is in the left, this means that u could be even strictly negative at a boundary, even strictly negative, not exactly 0, but in this case, it is the equation that somehow the super solution condition should hold up to the boundary. This is something I described in stationary yesterday, but it also can be done in evolutionary. And so for people that are used to classical solution, this is what they would call continuation after blow up. So sometimes you have a blow up in classical evolution parabolic problems, and then you wonder, is it still possible to continue the solution in a weaker sense after blow up? This is exactly a continuation after blow up. Why? Because until the solution is classical, of course, it coincides with the viscosity solution. So it's clear that since the viscosity solution exists for all times in this generalized version, this is exactly the continuation after blow-up of the classical solution. In fact, there is a similar, say, long-time convergence was proved by people in viscosity solution. In particular, there was a student of Guy Barle, Tabet Chamba in 2010, and then also Barle with Quas and Rodriguez came back on this question later. A kind of result similar to what I described before when P was, you see, P was bigger than 3/2 for me. So to some extent, even P bigger than 2 is still a similar result can be shown in the sense that if C0 is positive, U of t converges uniformly to the stationary solution, and if C0 is non-positive, then you have this sort of translating profile of the U minus C0 t is converging to V, and V is a solution of the ergodic problem. Of course, now both C0 and V are related to the problem with P bigger than 2, the super quadratic problem that I mentioned yesterday. But that problem is characterized. You have a unique solution, unique constant C0, unique solution V, so you have a similar result. However, it's very important to notice that this U that is converging in long time is the unique generalized viscosity solution. So it might have lost the boundary condition, much before converging to having this limit. So in fact, the previous result does not truly explain what happens if P is bigger than 2, because even if you assume that U0 and F are smooth, it's true that a generalized solution exists forever in viscosity sense, but of course we would like to understand when and how maybe the solution has already developed boundary singularities, and also if and how the solution has lost the boundary condition and what really happens at the boundary behavior. So in fact, I'm going to discuss those two questions now in the rest of my lesson. And to understand those questions, I essentially will stick to the very model case, to the simplest equation, because I want to give a little bit more precise descriptions. When F is 0, it makes completely sense. The two questions are still absolutely important. And also you have to forgive me because somehow because of the fact that, of course, I'm taking the slides a little bit from some of my works. Everything was described in the reaction case. Of course, as I said, this is just reversing the sign. So now forgive me, I will push the nonlinearity to the right, which simply makes the blow up in the positive sense, which means that eventually the problem now comes when U0 is positive and no longer where U0 is negative. And the problem will come if U becomes too positive. Okay, it's just by switching a little bit the sign, just forgive me that. But I think it will be clear. I want also to say now, switching the representation formula from minus U to U, of course, the inf becomes a sup. So now for this problem, I want to rewrite for you the representation formula because I want to explain once more that this representation formula gives really an explanation of, for example, the phenomena of loss of boundary condition. Why? So U here, U is described as a sort of a maximum of some functional. There is a control, so you have your stochastic process. This stochastic process is very simple. It's just a Brownian motion plus a drift. A drift, it's like a wind that is moving the stochastic, the Brownian motion. But this wind, this AT is your control, okay? And you want to maximize. So you see what you are maximizing depends on U0, and there is a price you pay for using your control, okay? But the problem is that since P is bigger than 2, this conjugate exponent here, P prime here, is smaller than 2. So somehow you are paying less than usual. The bigger is P, somehow the less you pay for a very, very singular control. In particular, if U0 is very, very large at some internal point, suppose that U0 is even a C-infinity compact support, but as a large peak somewhere. Of course, you want to maximize, so you would like XT to go and catch this set where U0 is very, very large because you want to maximize. It's like a bancomat, okay? You want to retire money in this bank, and this bank is inside the domain and you want to go there, okay? But to go there, you need to push strongly your Brownian motion because otherwise the Brownian motion will exit the domain. And then you need to push and you need to use the control and then you pay this price minus. But still, it is possible in some cases that even if you are very close to the boundary, suppose you start at the boundary or even close to the boundary, if you start close to the boundary, it may still make sense that you go and you push your xt inside, so you do not exit, you push xt inside, and you want to go and look for this point where U0 is very, very large, and you are you are aware that you are going to pay a price, but okay, you say, I will pay this price. It's maybe not too much of the price because the game, I mean, it's convenient for you. And if you do that, you start near the boundary, but you may still have u strictly bigger than 0, which means that the boundary condition is not 0. And this is an explanation of what happens. But now let me go to the mathematics and not to the economic explanation. So the mathematics is also very transparent, because this is what I was saying before. If u0 is large, you have surely loss of boundary condition and blow up of the gradient at the boundary. This is a classical argument. You multiply by the first eigenfunction of the Laplacian, and you integrate by parts, and you want to use the coercivity of this term. And this is why I have it in the right now. So it's a little bit easier, like in the reaction problems. I use this coercivity. And suppose you had kept the boundary datum 0, but then you have Poincaré inequality. Okay, so this is bounded by u to the k, and then you use here, this is Poincaré constant. You dominate with the gradient, and then up to multiplying by Helder inequality with phi1, and then a reciprocal of phi1, you do Helder inequality. But still, if you choose k not too large, still this guy can be bounded, because you know that the first eigenfunction behaves like the distance to the boundary. And then you plug this inequality in the above here, and then you build a typical ODE inequality. Why? Because this is essentially this is the derivative of what is in the right. So this inequality is of the time phi prime bigger than phi to the p, okay? And this would lead to a blow up if initially you have started too large. And this, what does it mean? It means that there is something wrong. And what is wrong? It is wrong that you supposed you could use Poincaré inequality. And though this means that you could not be 0 anymore at that time t, and also that the blow up, of course, the gradient must have blown up. Otherwise, everything remains, of course, controlled. And but there is something that we observed with Enrique Zuazua in one of our papers. We were motivated by a different kind of problem, but we needed some control in the long time behavior, and we discovered a very interesting fact. Because of the 0, you see, this is very easy. We started by observing that if we don't have the right-hand side f, and we have just the pure problem I am mentioning, then it's true when time goes to infinity, u is convergent to 0. And we could prove that it's even an exponential convergent. So we started say, well, I mean, it's very reasonable that u in the end is maybe it's still taking the boundary condition. And in fact, this is true. There exists a time after which u is certainly taking the 0 boundary condition. So in fact, even if u0 is very large, even if you had lost the boundary condition, that's a very surprising phenomena. You will recover at some point this boundary condition. We can quantify this T0. It's proportional to some universal constant k. It's proportional to the L infinity norm, or to the size, if you want, of the initial datum. And then we have that u becomes classical again. And the key point is to use a super solution, which is built as a sort of a stationary function, which is roughly the distance function, and translated in time. So we realized that there was this super solution that after some time, in fact, takes the 0 boundary value, which means that u itself also must take this 0. Of course, you need to use the comparison principle until you are allowed to use the comparison principle. And of course, we justified all that. But so it's a very interesting phenomena, because whatever U0 is, there is a sort of recovery of boundary condition. I remember very well when I talked to this in a seminar, and Philippe Soufflet got completely struck by that. And in fact, we started working on that, because in fact, of course, now there is a new thing to describe, not only blow up, but also somehow recovering of the boundary condition. So with Philippe Soufflet, essentially, we started working on this fact. And first of all, we started by giving a blow up rate and also blow down, if you want, so regularization rate. So now in the story, you will see a blow up time T star. This is the gradient blow up, and I will discuss if it also is the time of loss of the boundary condition. And there is a regularization time, which is the ultimate time after which the solution will go back to be classical. Of course, for this, I am using the model problem where f is 0, so you will go down to 0 necessarily. First, we show that there is a minimal rate of blow up, and also the same rate is also the rate of somehow blow down. So T here is smaller than the blow up time, and here T is bigger than, sorry?
I'm sorry, don't worry.
Okay, so there is the same kind of blow up somehow and smoothing time. Okay, maybe I'm skipping the proof, it's just kind of ODE, but what it's important is that the minimal blow, this is just the minimal blow up rate, but in fact, the rate can be faster depending or not whether the boundary condition is also lost. So remember that singularity of the gradient occurs at a boundary. So this gradient blow up only occurs at a boundary. So at the same time, you wonder whether you immediately lose the boundary condition or not. And this is what we exploited with Philippe in one of our papers, is that first of all, we made precise that this loss of boundary condition could occur more or less arbitrarily. So you can somehow build initial data for which the loss of boundary condition occurs everywhere, or you can fix an open set of the boundary, and you somehow can more or less have the loss of boundary condition only around this open set, so more or less in this open set. So more or less you can prepare the initial datum U0 so that the loss of boundary condition occurs at any open set of the boundary. But what's more important is that the gradient blow up may also occur without the loss of boundary conditions. And the typical situations where you observe that is with a sort of say parameter moving case. Suppose you fix U0 and you consider a constant mu times U0. And since everything depends on the size, more or less, you realize that in fact that should be a critical value mu bar, which is the infimum of mu positive, for which you have blow up at some time. So typically, if mu is very large, mu U0 will be very large, at least somewhere. U0 is not identically 0, of course. So at some domain, mu U0 should become very large. So you can slow down now, lower mu until you get a sort of critical value mu bar. And at this mu bar, you in fact understand that the corresponding solution u mu, first of all, blows up if and only if mu is larger than or equal than this mu bar, but you see loses the boundary condition if and only if mu is strictly bigger than mu bar. So in fact, there is exactly one threshold where you have a gradient blow up, but not yet you lose the boundary condition. And in corresponding to that, So this is a kind of minimal blow-up solution and no minimal blow-up solution. And these minimal blow-up solutions usually have faster blow-up and blow-down rates because they can somehow, the gradient can blow up, but also be immediately regularized. Okay, we don't have a general description of this phenomena, but in one dimension with Philippe, by taking initial data U0 with kind of bell shape. Okay, so I probably was meaning to put a picture, but the picture do not appear, I'm sorry. But it's a kind of bell shape. So you can imagine in one dimension, you fix an interval, you take U0 kind of a bell, and then we can describe what happens quite precisely by using tools like zero number a la Matano, if you want, a la Angenant, and arguments like that. Lap number and zero number. So in 1D we can really describe, and in fact what we can observe is that the minimal blow up is equivalent in that case to not losing the boundary condition, and that solution undergoes somehow an immediate smoothing after the blow up time. So it just blows up at the gradient in one time and then immediately goes down. And in that situation, the blow-up rate is faster than what we had estimated with Philippe in general. So this means that really the blow-up is faster. And recently, Philippe with Amala Touchy gave concrete examples where this rate is doubling somehow the usual minimal rate. It's 2 over p minus 2. And by contrast, there are non-minimal blow-up solutions, and in this case, you lose the boundary condition. In this case, the blow-up occurs at the minimal rate, so the velocity at which ux blows up is exactly 1 over p minus 2, and also the regularization occurs at the same kind of velocity for the gradient. And we also have a description on how u somehow detaches from the boundary, which means that and how it reconnects. It's linear, essentially, with a linear velocity in time. And okay, and then later it will become again smooth. And in the interval where the solution, this is maybe interesting, in the interval where the solution has lost the boundary condition, it's exactly like the stationary singular profile. It's typical like the, so sorry, this is, sorry, there is a mistake here. This would be the gradient, which is singular, while the solution is Hilder. So it's just this plus 1. And there is a picture, however, which describes this kind of one-dimensional result we had with Philippe, which is that if you start by 0 with a sufficiently, say, a typical, for example, initial datum like bell shape, then the solution starts growing at a boundary, and then at some point the gradient becomes infinity. So the solution becomes vertical here, and then the minimal one would immediately go down and become smooth again. The non-minimal one does what you see here, leaves the boundary condition and remains with this infinite derivative like the singular solution of the stationary problem. And then at some point it goes down again and recovers the boundary condition with the same rate as when it was lost, and then it remains smooth. And if you want to justify, I mean, why it needs some time to go down, you should go back to the formula of representation, because in fact, if you go to the formula of representation, you see that there is a competition here. U wants to maximize. I mean, the guy who is controlling wants to maximize. And of course, he would like to take the areas where U0 is very large. But of course, you see the price that he pays depends on the time interval. So the problem is that, and sorry, this is tau x minimum with t. Okay, so this tau x should be tau x minimum with t, because you can stop at t, of course. So you see, you pay a price, and at some moment, the problem is that you are paying this price for too long. It's no longer convenient. So you decide somehow that this idea of going inside and catch the high values of U0 is maybe convenient for some interval of time, but if this interval would become too long, this is no longer convenient. And this is why it's after some time you might be willing to change your strategy, because for the control problem, this is just a change in strategy. In this period here, what you do is that your strategy is to go inside and try to catch more or less what U0 is high. But then you change your strategy again and you say, okay, no, this is no longer useful. I must say that Philippe went further in this analysis. He was absolutely fascinated with that. And with Mizoguchi recently, they have proved that you can build not maybe easy U0 bell-shaped, as I was saying, but you can play with U0 and you can have this loss and recovery of boundary condition as many times as you wish. So you can have solutions that blow up again, blow down again, blow up again. You can really build very weird examples of solutions. And also Philippe with Roberta Filippucci and Patrizia Pucci came back also to the profile of the blow up, describing a little bit more precisely what happens in the normal and in the tangential direction. We also had done something with Philippe in 2017 for the case of single blow up, but okay, this is maybe another story. Okay, so I'll stop here. So of course there's a long list, but it's still of course not exhaustive, but in this case I will also prepare that for the first lecture later, okay, so I'm stopping here and I thank you for your attention.
So yes, really, Alessio, very good explanation of this losing of boundary condition. Really, yes.
Okay, I have a question. Yes.
Yes, just now, of course. I would like to stress that it is really very clear why it happens, because the contradiction, because different influence of unilinearity and gradient nonlinearity, different. They have different relation with this value of U, because really absorption and the source zone, they can do change very strongly and generate such a phenomenon. Excuse me. Laurent, please say.
Yeah, well, first observation that the last result you have with Philippe is absolutely wonderful and incredible.
Thank you.
Okay, I would like to ask you, the blow-up set, is there any kind of genericity of the fact that it is a single point or not? Do you have some hope like that?
Okay, so the problem is that the continuation after blow up is a continuous solution. So this means, for example, that of course you cannot have too weird in terms of the loss of boundary condition. So if you are the picture that you see, of course, is one-dimensional, but if you are in multi-D, this means that you need to have, if you lose the boundary condition 0, you must at least have an open set around where you have lost it. This is by continuity of U.
At one point.
Yes, sure, because U will be continuous.
Yeah, but the question is, if you have do you have, generically speaking, do you have a just single point blow up or not?
Of course, okay, we must distinguish, Laurent, if we are talking about the gradient blow up or the loss
of gradient.
boundary.
No, it's a gradient blow up.
Okay. So not the loss
of the gradient blow up.
Okay, yes, for the gradient blow up, you may have single point blow up, and this is something that Philippe had studied first with this with Lee. Then we came back with Philippe, and you see in this slide precisely, you see that a possible description of the singularity that you observe at a single point blow up. So we are in 2D here, X and Y in this formula here, X and Y, so we are in 2 dimensions. And the single point where you have blow up is the origin, of course. And this description that we proved under some conditions, unfortunately, because it's very technical, I must say, showed that the tangential profile was more singular than the normal profile. And but we were able to prove that only for some range of exponents p bigger than 2. And okay, generic, I don't know what you mean by generic in this.
Well, that means if you if you take at what kind of initial data, so except that maybe on a set with I don't know zero measure or zero or small measure, then the blow up point of the gradient is just a single point.
No. This absolutely I don't know. I don't know. I mean, this kind of, okay, so no, this I don't know. I mean, I'm not sure that the blow up of the gradient should be just in a single point. I mean, it could be in a much, I think, more involved set.
Yeah, you can. Yes, you can construct, but for parabolic equation ut minus delta u plus equal u to the p, I think it's a result. I think of what Velasquez. I think that it is you have genetically you have just a single point blow up. No.
Okay, this I don't know, to be honest. I mean, it's true that for the nonlinearity of power type, I mean, there is a full. There is a word of examples, and okay, what you say, I mean, of course, maybe it's true. I don't remember this, but for the gradient, I think much less is known, and even the possibility that you might have a single point blow up. Of course, we used somehow prepared a class of initial data that have, I mean, a sort of a bump in one point in a way that this leads the single point blow up. But I don't have an answer to your question. Of course, you should ask Philippe, who is really the specialist in this.
No, Velasquez, I think.
Yeah, of course, Velasquez. Well, of course, we even our result was very partial, because the thing that I am showing is only for p smaller than for p close to somehow is to some range. And the problem is that to go further, even I'm reporting a bit what Philippe was thinking at that time, you really would need these techniques a la Velasquez, which means a linearization around the singularities. And this is absolutely, I mean, not an easy task here, because so to be honest, we didn't, I mean, pursue that direction. But I, of course, I mean, the brave ones are certainly welcome to go in that direction. I think there is still a lot to discover, probably.
Yeah, really, gradient blow up is in some sense much more deep and much more interesting structure than nonlinearity of U, I believe. Really so.
Okay, and you said that if you take essentially any closed set on the boundary, bounded maybe closed set on the boundary, you may have gradient blow up on this set.
Yes.
This is. I mean, somehow what I said before is, for example, if you take any open set, more or less you can have loss of boundary condition there, and if you have loss of boundary condition, this is even stronger. So gradient blow up is for sure. Because you cannot lose boundary condition if the gradient remains controlled.
Okay, I see. Okay, it's linked to
so somehow this already says something. But of course, we only did that by saying that you can localize in any open set. Probably you are referring to much finer analysis of this blow up set, and this we didn't
Like
enter into that.
Like a curve or something like that. You can
Yes,
imagine.
exactly, like something, yes, much more fine. There might be still questions of capacity, because I mean, still these are more or less like a version of this is not too far from the point of view of the gradient. This is more or less a semilinear equation with a power, and once you understand, as now we a little bit do, and Philippe worked more on that the blow up is essentially in the normal direction, you can simplify the equation near the blow up, and probably you can try to use something that you know for the case of power nonlinearities, but for the gradient, of course. So, but to be honest, I mean, this I did not work on that direction recently. So,
Alessio, what, for me to do it more clear, because for gradient nonlinearity, there may be happen inner blow up in the domain. Only, I cannot imagine such a point, inner point, when happens blow up.
Yeah, the interior blow up can only happen if F is not smooth somehow, it's not bounded. And this, of course, can happen, but then would be the source F to, it's like a stationary somehow. So what I try to describe is more or less what I described is really what is totally intrinsic to the nonlinearity, because even if F is smooth and even if U0 is smooth, this may happen. But in this case, it could only happen at the boundary. But of course, if the source becomes singular at some point, then of course you can have singularities like in stationary problems.
Yeah. So not as I see this picture really, I cannot imagine only on the boundary, and the structure more or less clear structure of singularity maybe on the boundary for gradient. Really, some another picture with respect to absorption from which depends on you, not on gradient. Really, you explained it very nice with a very nice conversation. Very gave very many for understanding quickly. Now for me it became absolutely how we understand this mechanism, how it can look as such a singularity blow up for gradient nonlinearity. Thank you very much. Well, some question, maybe because we also three take part in this conversation, maybe somebody from the audience would like to ask. Please.